All right. Welcome to the first colloquium talk today in spring 2025. Very impressive. We have a lot of new faces. Really, I think it's a setting today. I really ask our speaker to talk very briefly about his experience because Professor Mark Meisel received his PhD in 3 years in Northwestern University. I don't see in the United States how many people can beat this record at. And I really want to spare you 1 or 2 minutes to tell our youngsters, if ever helpful, because I think it's a very important piece of story to our youngsters. I mean, at least it inspired me a lot. Anyway, long story short, Professor Mark Meisel is a professor from University of Florida since 1986, after receiving his PhD in Northwestern University and being a short-term postdoc in Europe somewhere. And then also he has been also director of high magnetic field, low temperature facility in Gainesville for a while. So he's a very busy person. It's my great pleasure to have him here today because this semester he's on sabbatical. Right after this, he needs to head to Europe for his sabbatical time. So what I want to tell you one more thing is he's not only a great scientist, a great professor, he's also a great collaborator. And I really want to say this words in front of everybody. He's really helpful and really kind of a great person to collaborate with. He's basically working as your colleague here. So this is really kind of appreciation I want to tell you guys about how wonderful to have great collaborators around you. This is basically part of the success of your career. That's my words. So today he's going to tell us some kind of, I really like the title, how are discoveries made, we are doing condensed matter. I guess this is the word coming from Mark.
Thank you. Thank you. Well, so thank you for that introduction. I'll use my opera voice. If you can't hear me in the back, let me know. Those very kind words. Actually, prior to starting my academic career at Northwestern as an undergraduate and then staying there for my graduate studies, as in kindergarten and first grade, and then the start of second grade, I lived on the Isle of Palms. My father was in the Navy. I remember my mother driving over to Sullivan's Island, and then my sister and I had to be quiet in the car when she went over the big bridge to Charleston. So, but my heritage is to be from Nebraska. My father retired from the Navy long enough for me to go to high school in Nebraska, and we would go there regularly. And so then I'm first generation, since you asked, I'm first generation college student from my family. And so I was lucky enough to get into Northwestern with a financial aid package and drilling water wells across the state of the eastern side and the eastern side of Nebraska and the western side of Iowa to make lots of money in the summer and then quit my job so they didn't have to give me severance pay. And I would do that in the summers to make sure I had pocket money for Northwestern. While I was also working in the cafeteria, I was a work study student, and I started working with Bill Halpern's group my sophomore year. And the reason why it was my sophomore year was I was a walk-on football player my freshman year. So I stayed busy most of the time, but I have a Bachelor of Arts in physics, almost a minor in untranslated, I should say translated Russian literature, pre-revolutionary Russian literature. And as a part of the BA program there, you have lots of opportunities for electives. So since I was paying essentially my own way through school, I wanted to be very efficient and decided I wanted to go to graduate school after the first year, started working in Halpern's group. So I decided to package everything so that my senior year as an undergraduate, I took the first year graduate courses. And then they made me an offer I couldn't refuse. I could stay there on a fellowship. I never had to TA. And so and the fact that I was an undergraduate worker and worked in the machine shop and had trained in the machine shop and got the cryogens and knew everybody else in the department, I was very fluidly already a part of the fabric. So really on paper it says 3 years, really was more 4 years, maybe 4.5 depending upon how you count. So, but along the way, it's the people that also made it important. When I first went to Northwestern, I thought it was me against the world because that was sort of the environment that I was built in. I would study all on my own. I learned maybe these issues of becoming a collaborator when I worked in such a group that tidied things together, connected people to solve problems. If I give the high energy group some nitrogen when they need it, some liquid nitrogen, then maybe they have a sheet of Kapton tape that I need to finish my cryogenics.
Trading, huh?
Anyway, so that's a condensed version. I tried to have a pun here. I don't know. Someone once told me, don't say that you've tried to tell people you had puns. So this is trying to have a pun, but really it's trying to speak this idea of making discoveries and having to know how to find them or get them. Also goes back to equipping students with their critical thinking skills so that when they have an opportunity to put things together, they can actually also see it and do it. And so ultimately, in this day and age, it might boil down to what is science, because I actually find that science is under attack in my definition of science. And so that's really the simple question that we all need to be prepared to answer. And I think at the end, I'll just simply say, I encourage you to have your answer when you're asked what science is. So one way I might go to look for what science is, my wife she's a molecular geneticist. I'll mention her again near the end. And she wanted to get Science Magazine. She had already been getting Science Magazine when I met her. So we get the hard copy still at home, but these come from the web. And she doesn't read it. I read it and I tell her what's in it. So if there's anything interesting in her field, she'll read it. So you might know that Science Magazine has, for a number of years, the breakthrough of the year. I don't know if breakthrough means discovery, but this is the most recent one, 2024, a new a vaccine for HIV. This is 2022. I like this particular web display because I once heard when I was teaching modern introduction to solid state physics that the governor had said that we need to stop studying other things and focus on Western civilization and everything Western. I didn't believe it when I had heard it on the radio, but then I went to see the video clip of that press conference and he said it. I don't believe that was artificial intelligence. I think he did say that in the time. And so at the time I was talking about quasicrystals. So I talked about the web unfolding. National Geographic actually has a cutout for you to do it. And the origami inspired, and there's also a NOVA program on it also, origami inspired Eastern art that actually spirits it gives some motivation to that architectural folding and packaging that allows the Webb telescope to unfold in such a way. So my point of view, as it comes along, just to tell you up front what the bias is that we come together from any walk of life, of any type of cultural life, to come together to share our experiences and use our voices and have some impact in making the discoveries. Here's one about AI, 3D proteins. Here's one about Corona. Of course, it impacted us all. And congratulations to the junior people in the world. My senior career can tolerate that, but I've seen some students and also junior faculty members really be burned out on the coronavirus episode. Let me tell you what I do. From the main part of my work today is that I am the director since August of 2019 of the High Magnetic Field Ultra Low Temperature Facility of the National High Magnetic Field Laboratory. These are my colleagues in faculty, postdoc, engineer. This is the group that comes together in a building that was built some time ago when I actually came from my postdoc period to Florida in the time before the internet, trying to find a job back in North America as a research scientist. And 2 years later, I became an assistant professor in which we built 3 shielded room bays in a small building specializing in low electromagnetic interactions so that we can now offer as a part of the Mag Lab, as it evolved, users a welcoming and comfortable environment for their work that they can't do in their own institutions. Now I want to also specify something that it was actually very inspiring to me, because I haven't also always seen VPs of research do this, But that particular grant was for two instruments. The money was being provided by the University of Florida for the building, and the founding PIs, Dwight Adams, Gary Ias, and Neil Sullivan, convinced the VP for research, Don Price at that time, and he deserves to be mentioned because they built a third bay. Normally, I've also run into later in my career, hey, we've got the grant now, can we just have a little bit more money to make it even more special? And the VP for research says, no. In my mind, taking a minimalism approach. Whereas Price banked on us being able to get additional funding. So this particular bay, this shielded room was fallow, built with Gatorade money that comes from that account. And then a few years later, when the Mag Lab was being proposed to be moved from MIT to Florida, there was this bay, it's openness and ready to be used, that became the first part of the National High Magnetic Field Lab. That's a part of this idea of how do you make stories that actually means all the tools are around. You need to equip everyone that needs to find those things and do it all together. And we have great shops and cryogens and the rest. Now, when it comes to actually giving a colloquium, I worry. And so some of you may remember David Merman's What's Wrong with Those Talks. So what's wrong with this equation? It's not punctuated correctly, for example, or numbered properly. Here's, maybe I learned this when I was graduate coordinator, piled higher and deeper. So here's your bingo we would play sometimes. We've all heard some bad talk, so I actually decided I would Google AI to tell me what a bad talk was, because I don't want to give a bad talk. And so talks are, and then also my wife was invited as a part of her research to give a TEDx talk. And why are TEDx talks only 18 minutes? Because basically that's what I really can retain. Well, sometimes I understand in lecture, also from a 50-minute lecture, but also in the sense that I've been trying to actually get our department to maybe engage in a new way to actually give a 20 to 25-minute talk, 5 minutes of questions, and then we go and have cold beverages of your choice after the reception the coffee and cookies at the beginning. Anyway, so what's wrong? It could be that I go on too long or I'm not prepared. I'll look forward to you grading me later. But let me just give you my rubric, because I went recently, we had Paul Steinhardt from Princeton University give the second kind of impossible in early 2024. Absolutely riveting. If you ever get a chance to hear him speak, do not lose that opportunity. It's also a book now. He's written a book about it. I think it's a whole NOVA program on its own, or some science program. It's absolutely riveting of finding Earth-made or quasi-crystals in the terrain here, in the regolith here. And then lastly, this is in the digital age, that's recently. I go to the plastic age, that's when we used to have the view graph file. I know this sounds like the days before the internet to most of you. When I was an undergraduate, starting when I was an undergraduate, I heard Michael Turner for the first time. I've heard him many times in my career. Absolutely stunning communicator of why the cosmos is so fascinating. In addition to his slides and talks, so I give him kudos. I say these are the best colloquium speakers that I've ever attended. Well, let's just continue. 2017, breakthrough of the year, multi-messenger detection of two-neutron merger. That's absolutely fantastic stuff. 2016, this is the LIGO. This is seeing and detecting gravity waves. And then I want to just skip down to 2012. You can't really read it. It's normally the third week of December. It's in 2012. It's, of course, the discovery of the Higgs. All the things that I've mentioned so far that made breakthrough of the year seem to be at some initial level, on first look, a discussion of big groups coming together to solve problems and making that advance. But let's then skip to December 1995. It was molecule of the year, and it was Bose-Einstein condensation. Now, it just turns out that in the same issue in which this is written in December of 95, you'll also see the runner-up as the master control gene of the ILIS gene. And I had already known about that. I mentioned that my wife already is a molecular geneticist. And also, I just blow up this. This is not really. This is artist conception. This is more of the real data of the cover of the report from Wyman and Cornell's group at the time. And Imagine back in 1995, I'm on sabbatical. That was the last sabbatical I took, so I think I earned one now this semester. And my wife and I have a less than 1-year-old at daycare. She's also employed at Northwestern University. We went back to Northwestern. We're in the car, stuck in traffic, trying to pick him up, our son, before daycare. And an interviewer comes on and talks about being able to grow eye tissue at any time on Drosophila, fruit flies. And I'm riveted. And the first thing that comes to my mind is, how did it work? She asked the question, the interviewer asked the question. And it's the researcher from Walter Gehrig from Basel, who says, oh, what we do is we take the master control gene, we inject it at the right time of development, and then we see the eye tissue on the Drosophila. And we can see it on the leg and the wing. And she said, well, on the leg and the wing? Yeah, it can be on the leg and the wing. Next question, I'm driving, I'm not even talking to my wife. We're both riveted on this conversation. What does the eye tissue look like? Well, it really looks like the eye tissue that shows up there. And then it's, wow, that's really impressive. No, he said, no, that's not really the impressive part. Well, do indeed, what is the most impressive part? Now we take the master control gene from the white mouse lab rat, and we take the gene from that mammal, and we insert it, and we grow eye tissue at the right places. We're still driving along. Now, the next question that's in my mind is, mouse eye tissue? No, not mouse eye tissue. It's real Drosophila fruit tissue. Wow, what does that mean? That means that somewhere back, that master control gene that turns on eye-growing tissue, the theoretical prediction of such a master control gene is now textbook ready for being placed into the literature, where insects and mammals had a common heritage. Wow, that's really stunning. That's a great discovery. Did it just happen in your laboratory, she asks? Oh, no. I've known of this possibility for about 15 years. So, well, why did it happen only to discover it now in 1995? Oh, well, I get a new person in my group. I explain to the new postdoc or the new graduate student that this is something that they might do. And they choose something else. And finally, so this one postdoc said, well, I'll give it a try. Boom, and it happens. So for me, working in superfluid helium, regular superfluid helium-4, Bose-Einstein condensation of helium-4, Bose-Einstein condensation of atomic gases wasn't really as spectacular. I thought this should have been it, but it only came in second place. Now, this issue with respect to the Bell tolls at Bell Labs was this, on the same sheet of paper of that issue of Science in 1903, page 1903, they talk about the Bell tolls for AT&T Bell Labs splitting and ending its operations in the known way. Well, so then I should Google, because this I find fascinating, and I want to use this as reference one throughout my book, this book throughout my talk, The Idea Factory by John Gertner in 2012. I gave this talk initially, started giving it when my Slovak colleagues asked how can they improve doing science in their own and make discoveries like Bell Labs did. And I said, well, maybe we should look at the history. I don't walk backwards through life. I'm always looking at the history. I'll walk forwards, but I peer over our shoulder to try to learn lessons from the past. And so I want to draw upon this in the talk, some aspects of how Bell Labs actually went forward with it. And I also say, 100 years ago, it's reformulated itself as Nokia Bell Labs, January of 1925. They say they've been at it for 100 years, but it's also changed shape and style over the time. So if I go today and click on the web page, you see these very modern optics and things. They see quantum innovation. This is my field. I live in this world of this type of discovery. All things AI, going to the moon. This is some of the things that my wife is working on. And just general research for being sustainable and the rest. So very modern topics. But I want to actually just give you the punchline now. I want to give you the punchline that I'm going to try to actually substantiate, and you can actually then be a judge of yourself about a look back at Bell Labs. How did they do it? I'll tell you the rubric in a moment. But first of all, this is the first president of Bell Labs, 1925 to 1940. He was president. And he basically was making the point that he wanted an industrial group. The spirit of it was that this industrial group coming together from many different disciplines and having an open door policy that 20% of the time you need to be open-minded to anybody else in the team coming to ask you questions and to work on anything you did. But of course, you're also assigned to some other group to solve some problem. And the issue is that he's saying there's basically at Boyletown, there's plenty of good ideas out there, almost too many. Mainly they were looking for good problems. I saw a cartoon from XCD. This is good and bad ideas or good and bad problems. Maybe you've seen it too. So this actually started when I was a Fulbright scholar at Košice at Shafiric University. And for me, just to give you that punchline, the leadership sets the culture. The framework, I've already mentioned, the VP for Research allowing that third bay to be there for us to go on to then be able to use those facilities. It's a partnership, just like teaching a course. I tell the students, it's just not me against you or you against me or you against the world. We're partners in what's going on here. Please tell me what you're not understanding of the material, along with me telling you what I think the important points are so that we can make progress. Now, since I mentioned being a Fulbright scholar, I want to also mention William Fulbright, because William Fulbright draws upon his own history of being from the interior of our country, that would be from Arkansas, that he grew up in Arkansas and he had the opportunity to become a Rhodes Scholar post-World War I in the UK. He was able to then travel and see post-World War Europe and was really devastated by what was happening. And so when he became a senator from Arkansas and saw the aftermath of World War II, he was dedicated to bringing together a program which would give the Fulbright system birth as funded by the United States government. And so this was his vision, once again, leadership leading the way for facilitating people to expand their horizons to be able to solve problems. Now, we need a rubric. So most of the time you want the rubric to be quantitative. Why did I get these points off on this paper or something? So I just present it not as the rubric, or anything I'm saying is not the answer or the way to think. It's a rubric. It also depends upon how you count, because different people will count. Were they really at Bell Labs where they did all the work? Did they come to Bell Labs and then win it? Did they work at Bell Labs and then go win it when they were somewhere else? But here's just a large number of Nobel Prizes that have been awarded with people associated with Bell Labs. And we were talking earlier about radio astronomy, Penezis and Wilson in 1978. And this was a Nobel Prize awarded when I was an undergraduate that I found really inspirational, a story that inspired me, thinking about, really? I mean, is that how it was done? That is so cool. But then again, you could ask about a number of these different things. And at some level, when you look at any of the things that are going on, and also I want to mention machine learning and artificial networks with respect to detecting sound in music and the rest, it's all it's more complicated than we know at some level or could expect. And when I put this all together, and here's Osheroff, Richardson, and Lee with superfluid helium-3 in my world, it's interesting to try to think about how it actually happened. But at least as a standard with people, the transistor and the rest, we think that it's actually there. So let's go back to the original history of Bell Labs, because it's so reminiscent of what actually is going on today. First of all, you have an inventor. Here's Alexander Graham Bell. He gets 2 patents, and then what does he need? He needs venture capital, so he needs financial backers. Oh, well, when the financial backers come together and say, we want to fund you to do what you're doing, well, we need somebody to make the equipment. Well, then you go out and buy and acquire another company. A hostile takeover? These are the things of that actually go on today when you think about new startups and the rest. It's just history repeating itself, but at a different time. It's really the same aspects of what's happening. And so, how was it then accomplished when all of that is packaged together? I want to come back to leadership and culture, because here's Theodore Vail, president of AT&T, starting in 85 to 87 and coming back again just before World War I. And when he becomes in 1907, he says, look, I'm back. What we need is a philosophy. We need some core values. We need some sort of organization to remind us regularly what we do as a team in order to find out what's happening. One system, one policy, universal service. This was easy to facilitate and be in place because it was reinforced by the government, because they wanted a single provider of communications in a military theater, because World War I was just absolutely a debacle for understanding what was happening, communicating in those operations. And so this married and mixed really well in. And I remember as a child asking my father why we had to actually buy a Bell phone when some new phones were starting to appear on the market in the late 60s, early 70s. Now, I've already shown this slide. I just want to remind you about the fact that it's not an idea of the good ideas alone, or running into the student who asks lots of questions. What's better is the student that comes up and asks a question they've really thought hard about. It shows that they're actually thinking about it. And that's the way I think of good problems. Good problems are good questions, and good problems. This is coming together to actually do something that's going to justify why you're actually working on that, with respect to how it whether you were making financial reward here, or maybe as a junior professor can actually get funded for it, or as you write a proposal for a fellowship, for example. Now, next person I want to mention in the 1930s was Oliver Buckley. I was absolutely stunned at about the time that my mother was born. I have to think about that. I think for the junior people, when I first started studying physics, I thought any paper that was published before I was born wasn't really worth reading.
Forget Einstein.
Yeah, exactly. 1905 just stuns, 1905, come on, Meisel, smell the coffee. But I had to be educated. I had to change my point of view. And here's Oliver Buckley calling in everyone to give them, who's been hired that year, to say, welcome to Bell Labs. Let me just tell you what your real task is with respect to the assigned jobs that you may be doing. Our job is essentially to devise and develop facilities which will enable two human beings anywhere in the world to talk to each other as clearly as if they were face to face, to do this economically as well as efficiently. This is the 1930s. This is science fiction at some level. This is science fiction with a vision of leadership, communicating to the people who are doing the work an inspiration for making it happen. Once again, it's not just top down. It's not all bottom up. It's a partnership of coming together and making it happen. Helping you finish your work for your PhD thesis. Helping you to engage other members of your search committee, of your PhD supervisory committee, not just your mentor, but the others, to read and help you take that thesis, that rough cut rock, and polish it into a gemstone. How did they actually achieve it? They were in New York City for a long time until they moved out in the early 60s. So this is the picture that I found here. I found this. Oh, I should also say, a lot of these things that don't have the S here, they're no longer, the Bell Labs Nokia didn't keep them in place. This comes from somewhere in my talk. I gave the citation of, I pulled a bunch of these in 2013 or so when I gave the talk and generated some of these slides at the beginning. This is what Google gives you today. Look it up. You can see the whole thing. Today on our walk over to the downtown on the other side of the State House, there's this building up to about here. I even counted the floors. There's 8 above this first break, and there's there, but it's only 2 deep. It's about two layers deep. It's maybe a hotel or something now. So the architecture still remains the same. But this is once again Buckley's words are quoted in this reference, this book. No attempt was to achieve complete siloing and isolation, putting physics over here, material science over here, chemistry over here. It was all blended. It was all blended so that you had to meet your colleagues in the hallway. When I visited Bell Labs to talk to Osheroff when he was still working there, I was stunned by the size of the narrowness of the hallways. He says, that's so you actually had to almost rub up the 2 people together. He says, it makes it hard to get the doers down the hallway for the liquid helium while other people are coming. And so it's really an attempt to bring people together, much like I think the colloquium is to do, to make the department and the college and the university and our outreach activities stronger. And share our ideas of, oh, I went to the high school the other day and I did this type of demo and it was a real hit. Well, tell me more about it, because maybe I need to do something like that when I'm out there. But at some point we have to give pause, because as a state university we want to know what the role of the government is. You know, I'm asking my colleagues in Košice, they would say, well, it must be the Constitution, the Bill of Rights, free speech we hear about these days, and a long time have been hearing about it. Free enterprise and business. Some people have, when I was trained, for example, I was hearing laissez-faire capitalism is the way to go. There's 3 branches of government: executive, legislative, judicial, how they're all intertwined, how the checks and balances are there. How are we supposed to actually think about this? I give Madison because he's sometimes considered to be the father of the Constitution. But it's at this point maybe I need to put the pause on, because I also gave a talk about engaging students in the educational process, one biased perspective. And I quote, transforming physics education. Here's Carl Wyman of BEC. I'm drawing the connections to a condensed version again of Nobel laureate fame for BEC discovery, along with one of his partners now and colleagues in educational physics at Boulder. This is from 2005. And I also I used to show a lot of Far Side cartoons until I saw that Gary Larson, had written an open letter asking that all his cartoons come home, that he didn't like seeing them used by other people indiscriminately, that he felt an attachment to them. So I don't show any, but this one was copyrighted by Physics Today, appeared, so I give those citations here. And so it's a question of perspective. If you can't see it from the back of the room, you might pause and take a look, or I'll read it to you. Mr. Osborne, may I be excused? My brain is full. And so, okay, well, let's see. There's Mr. Osborne, must be, he's turned it around. So there's some good news and some bad news, or bad news and worse news, if you want to. First of all, it's algebra. You might say, well, from the physics point of view, at least it's not physics. Well, I said, well, but algebra is our language in which we frame, mathematics is the language we use to quantify and describe our of things around us. So maybe that's the good news. And then you might say, well, look at the clock. It looks like it's right on the hour. Maybe that's at the end of class. So maybe it's on Mr. Osborne, because he might be one of my colleagues who's disrespectful to the schedule of the students who have another course to go to, or at the end of class on time. Start on time, end on time. Or could be just at the start of class. That would be bad news. But at least I see some people taking notes, whereas today when I go into lectures, sometimes nobody's writing down any notes. I get worried. Is anybody carrying what I'm saying? And of course, I have to say though, that picture right back there looks like me when I was an undergraduate. How did Bell Labs do it after that little interlude of thinking about how we discuss things? It was basically a monopoly. All of this issue of monopoly was that basically the Pentagon said and convinced Congress and everybody else in the legislature and the rest of the president that we needed that uniform one voice, and it could only be in one place. So it's the money that they got with respect to these, having exclusive rights to actually come up with that communication system. But First antitrust law was in 1913, again in 56, again in 82. So you can see that there's some decisions that there's, hey, it's too big. You know, it's sort of mimical of some things, all the social media things, Meta, the rest. It's history repeating itself at some level. And then in 1984, it officially ceases to exist. And then, according to the sources I give here, they claim 96. Here it says officially, this is December of 1995. So yeah, 95, end of 95, starting of 96. People were leaving. Art Hebbard comes to Gainesville, Florida. He was discovering buckyballs, for example, and working with buckyballs and superconducting buckyballs, I should say. Buckyballs that have been discovered there. And so things are changing. And so if we then look at the Nobel laureates as a rubric for judging the science and the culture that was in place, maybe we should also ask ourselves, what is science when we talk about the Schoen affair? Maybe some of the junior people here haven't heard about this in the late 1990s, or in the late 1900s to the early 2000s. Coming out of Bell Labs was a flurry of papers, with most of them being first authored by this individual. And there were eight of those papers in Science were retracted. There were 7 in Nature. There were a total of 32 retractions. This was just blatant fraud. It took time and energy. One of the junior faculty members, one of the graduate students, when I was on sabbatical at Northwestern, had become a junior faculty member in Canada, and had written and gotten funded for moving transistors on plastics and the rest, which is one of these papers in Science and Nature, or a couple of them, that were retracted and were just bogus. And his self-esteem took a blow. They're thinking that I just got all this money. And he even wrote to the agency and said, look, this is all wrong. Just keep it and do something good with it. You know, and that's what I said to him. I said, look, you're empowered. Don't let it happen. Make sure it doesn't happen again. And science has a certain level of integrity that we need to maintain. How could this type of scandal have come from Bell Labs? Art Hebbard had already moved to the University of Florida. You ask him about it, he's just totally stunned. He would tell you that before the breakup, when he was at Bell Labs, they had an internal culture of reviewing everybody's paper and being a legitimate referee. But when they went to the corporate version, the breakups in the beginning of the breakup of Bell Labs, so this is the late 90s, namely about 5 years later or so, it spreads like wildfire, spreads quickly, I should say, that culture is broken and it's lost its ability to have its checks and balances in place. Refereeing a paper is one of the hardest things to do. Refereeing a proposal is one of the hardest things to do. Even harder is writing a negative report and being constructive and objective to the best of your ability about why you came to that decision. It's hard. It's hard work that we do. But we also need to use our voices when we see something that's wrong. Now, I promised some sort of also some instances about aha moments, and then the theory comes later. Because many of the students think that that I've talked to, even before the pandemic, they think, we don't need to put any more. Why do we have to take the intro labs? You know, the intro labs are locked in the 1960s. I can agree that they're boring, but I find I can watch a pendulum go back and forth for a while thinking about different things, you know, or a spring going up and down. You know, but I'm weird, and so Cameron Onus, he got the Nobel Prize for not discovering superconductivity, but for liquefying helium. He was after. Here is resistance as a function of temperature. This starts at nominally 4 Kelvin and goes up to a couple of Kelvin more. And so this straight line that everybody had observed or nearly straight line, and how the resistant approaches t equals 0 was the big debate in the Cameron Otis lab on the banks of the canal in the heart of Leiden. And the university's moved out of there, but I was also a visiting professor in that old building. It was really an honor to be there and to think about just the question of how it extrapolates to t equals 0. Does it come in at a finite value? Does it plateau? What are the roles of the impurities? Maybe we need very clean metals, so they're working with mercury, and although they actually see a precipitous fall. But in addition, even to this paper, they talk about not saying that it's absolutely 0 here, 0 resistance, but that their dynamic range can't measure it. They can't measure something below, at that time, a micro-ohm. We think it's 0, but we gotta be honest, as an experimentalist, it's hard to measure 0 as an experimentalist. Actually, it can be easy if you don't plug the equipment in. I can get 0 too, but you have to teach people about dynamic range, and that's part of what defines science for me. For example, about our observations, because I believe it's an observational science and a theoretical one. So the BCS theory came along in 1957. Bardeen, Cooper, and Schrieffer received the Nobel Prize in '72, and this is one of the important papers that they had. But they actually had a typo in there, and they left the slide and they put in a little correction. You can't read it, but if you're really interested in it, they go back and correct it at least before it's printed in the text, but not the figure. I thought that was pretty cool. At least they caught it. But they were at Urbana-Champaign at the time working together. But since we're on this idea of condensed ones, that was for spin singlet BCS superconductivity, where the electrons are paired up and down for a spin singlet state. What about P wave or triplet superconductivity? So our colleague Miyano in Japan, and his group in 1994 took this ruthenate and said, P wave superconductivity in this system. And this is 94. Then they said, in 98, others start, if it's really true, maybe we can actually make some devices out of it and the rest. And so we go to 98. It's singlet triplet. They say they unambiguously identify it with the night shift that was originally found in 1994. And then this is Stuart Brown, my colleague, who was at Florida for a while, is now at UCLA. 1919, he's doing strain on these same samples, and he says, no, it's not consistent. The results that were published here are different than what we see. We see something completely different. Then, in order to actually continue the story, they do it in 2021, and there's a nice little description in Physics Today about how COVID enabled them. COVID enabled me to be a better communicator with Zoom. I have to say that. I became more fluent using Zoom. COVID made me become more sympathetic to impact on students and what's going on. And here the student says, we had lots of time, so we could go in very quickly to tune something and just watch and wait for long equilibrium and get big data sets. And they proved that what was going on here was that they were heating. They basically reproduced this with a very high level of excitation, and when they backed off and acquired signal for a longer time at lower excitations, they were self-heating to get this effect. And it's not reproducible when you do it the right experiment. And then there's this article in 2024. We still don't know what the superconducting state of it is exactly, but what is this actually happening here? Is it science? Is it part of science? It's done in the science realm. Is it self-correcting? Is it bad science? Is it good science? Is it the process of science? What is science? And then I just decided to leave this. I don't want to give any pictures, because this is the most recent one about high pressure, room temperature superconductivity by someone who was first author on a paper purported to have discovered, out of the Ike Severa group at Harvard, to have discovered metallic hydrogen, then landed a job in Rochester, University of Rochester, and was finding high pressure, room temperature, high pressure superconductivity. And once again, nature is retracting, and papers and the rest. The impact, James Hamlin is in my department. He's an associate professor. The impact on him is that Hirsch from University of California, San Diego, was asking him for the data of a paper that he co-authored, but was second author when he was a PhD student. He went on later, that was at the University of Washington, St. Louis, and then he went on to work with Brian Maple later. And when they went back, and his thesis advisor went back to the lab books, got the data, and they found that the first author, unbeknownst to the other authors, had improperly corrected the data to enhance the feature that made it look like it was superconductivity. So Hamlin retracted his paper, but on the basis of that was asked by several different agencies to investigate this work. And there's several different renditions, and I would say based upon the story that James Hamlin tells me over coffee or a different cold beverage, that this is correct. And the amount of creative energy that has been lost to actually discovering how the fraud perpetrated and got involved and providing that evidence to the funding agencies and to the general public is somehow negative in my mind. Also negative because now you ask yourself the question, is that scholarly activity? Busting the fraud on someone? Because he gets judged for promotion to full professor on his scholarly activity. Is it service to the field? How does one judge that? What is science? It comes together to ask us, what is science under all of those conditions? I'm almost finished, so I just want to tell you about one absolutely phenomenal person. Is he a discoverer? Is he an inventor? Is he an identifier? Is he other? I would say he's absolutely the amazing Shannon. Because he created, he's listed as a mathematician, but he's the inventor of information science. He's the one that pieced together information science and wrote a paper. And I think that original paper only has 13 references. And it's many pages, but it's only 30, because there's nobody else to cite other than Einstein on entropy, and a few other things. And so he defines a whole field. And basically, information science, information is entropy, and entropy is money. So if someone who doesn't believe me says, well, entropy, yeah, that's thermal stuff. We do that all the time. Need to heat your house? That's money. Or cool your house? That's money. So now you know where Meta and Google and the rest get money, because information is money. And he proved it. And then in addition, he wanted to do some machine learning, so he made a mouse, not digital, totally analog mouse, resolving a maze, and below here are a whole bunch of these switches that were used in the radio telephones that I used as a kid. It's absolutely phenomenal. There's a YouTube on it, and there's also, I believe, another a Nova or something about what he was doing with this mouse. But he's just absolutely. I just find it really. If you haven't ever been there, you want to look for something to really Google during a really bad colloquium, I suggest you have a look. Now, I promised to tell you about my wife, because I have another. Is it a discovery, or is it science? This is Elisa Paul. She's director of she's professor of molecular genetics in the Department of Horticultural Sciences. She's an Arabidopsis. She did maize when we met. She's doing Arabidopsis now, and so she's been doing space science for a number of years. And one of her papers that metrics, old metrics, these new metrics on how many people Googled it and all that stuff, or newspaper articles and the rest. A good science paper, or a condensed matter paper might have 200. A really good one. Hers is 6,000. And just to frame it, COVID in the same year, the crystal structure of COVID was 13,000. So her team took 10 years, more than 10 years, 3 different rounds of proposals to obtain lunar regolith from the National Library of Regolith from the Apollo missions from Houston. And she was able to grow for the first time plants in lunar regolith. Yeah, she's just answering the question. Will plants grow in lunar regolith? It's just not happy plants, sad plants, but it's the whole genome, every gene in here where they can engineer the genes to be ready or engineer the regolith to be ready and choose what's going on. But even before that, most recent work, they were doing work on the space station, not to see that there are these roots, and you may not be able to see them at the very back here, this is not great resolution. These roots are actually skewing, moving, not because of gravity, because it's microgravity, but they are in concert skewing. You know, these are conversations at breakfast, because normally we're alert at breakfast, or we're becoming alert, I should say. I make the coffee and the breakfast, and she comes out after the shower, and everything's ready for her. And she says, one time she said, they finally funded us. Okay, that's fine. And a few months later, it was raining, and I couldn't bike in, so she says, pick me up. I picked her up. She said, let's go water the plants. I really like the new door here. And then I went into the growth chamber, which is an appendage building, and everything was pristine. I said, I know what it is now. I'm in the room with the lunar regolith the plants are growing. She said, come over and have a look. I said, no, I'm not moving from the door. She says, why? I said, I don't want the headline to be physicist husband sneezes and ruins the experiment. So the skewing, now this is Darwin from a different time. And so he had conjectured or hypothesized that gravity was the reason the roots grow down. They skew in the direction that they do. It's not what's needed. They proved it's either light or gradients of nutrients. They'll skew under other reasons also. It's just not exclusive. It's not as though they're all going randomly. They are skewing without the gravity cues. They're turning on other genes to do so. And they know the genes. They can identify that. She's very careful to say Darwin was wrong. Because there's plenty of people that say that, for example. He's just simply saying this is an example of a conjecture that couldn't be completely tested until we got the right environmental laboratory space to do it. And when we did, we found more and learned more about it. Now, is that science? Is that science discovery, or is that just science, proof or whatever? These are the questions you have to ask yourself. But really, it comes back, I get from me as I wrap up, Fulbright, and he wrote to the president about the Fulbright program coming into law. And he talked about how man struggled to be rational with himself. I would say people struggle to be rational about themselves in the language that I would use. But involving coming to a constant search for understanding among all people and all cultures. And that search that can only then be fulfilled in a positive way, in an efficient way, without loss of negative energy to correct frauds in the field on a worldwide basis. So on that note, I welcome you to evaluate me on the rubric, and thank you for your attention.
It was truly educational. And yes, what's your evaluation to our speaker?
Stunned. No equations. I don't think there were any equations there.
Any thoughts, comments?
I just want to say, John.
I want to ask you this. It seems like you're concluding. Why is science are going to be worried about cross-culture and all that? Your last two.
Yes. What?
Yeah. Well, what's the relevance of culture, DEI, or whatever?
Yes. So it facilitates us to actually come together and solve problems quicker and more rapidly. Bell Labs did that.
Not culture.
So here's the this is my opening example. We're going to come back to the web here. Architectural inspiration from origami folding. That's a cultural issue. How that is a cultural one in which, if my culture is to say, put the blinders on and only think about Western civilization and Western art for our grade schools and high school students now in the state of Florida, I'm concerned that they'll not be able to make discoveries and move science along, or to be able to judge it appropriately.
So your point is to learn science from all cultures.
Yes, yes.
Different civilizations.
Yeah, so for example, I'm not, so I grew up in a world in which my father said, this is the answer to everything. This is the way you do it, don't do it any other way.
Naval
Yeah,
regulations.
well, exactly. There's the right way, the wrong way, and the way I'm telling you to do it. And then I would work with my uncle out at on the Missouri River, building the shed for, the boathouse. And my uncle would come along and say, don't do it this way, do it my way. Do it, and then my dad would come back and say, no, that's not how I told you to do it. And I said, well, my uncle's telling me something different. And so then I learned that was okay, because I learned to do it my own way, and I told them both that I was doing it the other way, that the other one had told me to do it.
You're doing Hendrik Shaw.
Well, there you go. Yeah, no, but I'm getting it done right. Come on, because it's a question we all have to come together to answer. If we really believe, for me, I'm a more complete person because I've read about the superfluous man themes in pre-revolutionary Russian literature. That made me reflect upon introspectively myself about how I went through life, or how my son has gone through life, and how the students around me, all of them are going through lives, and through the pandemic and the rest. And it makes me think about how I can actually communicate my science to the classroom. High schools, grade schools. Second graders are tough, but 3 through 5, I used to really focus them because they're really great.
I was about to say, as a precursor to the science openness and so on, the problem is you need this openness at the education level,
Yes.
starting from the classroom. And that's where you need more discussion and exchange of ideas, rather than sort of one unidirectional flow of information.
In one part of my career, I was involved in a promise program for about 3 years at Duval County, which is Jacksonville schools, very diverse set of schools system, huge. And we were charged with K through 8 teacher improving their science content knowledge, to make sure, as the American Association of Scientists had a brochure of the major myths that are being taught in the schools as science fact. And we addressed them, and I had a teacher stand up and said, there are only 3 states of matter, you're wrong. That, okay. And I, now in front of all, she was decorated because she flew on the Vomit Comet plane that NASA chose. I have to be very careful on how I approach her and answer her question, to try to build trust with the other people in the room. But you're absolutely right, because there's, there's been plenty. Another example, after I give a demonstration, the teacher says to me, can I talk to you? And she says, I'm teaching this next week. I only have physical ed. I forget what her field was, but it wasn't science. And she says, it says the boy throws the ball and it's left his hand and there's still a force on it, but I don't see it. And she's supposed to be teaching where the forces are in the rest. And so I said, and then I said, that's a common misunderstanding about that. Don't forget gravity. You don't forget the things that aren't there necessarily. And so that's the challenge. In order to equip our teachers with better science content knowledge and confidence to say, I don't know the answer. So really, if you're to say, Mark, what's your question or answer? I think I know what science is.
A magazine.
yeah, magazine cover, yeah. But in the context of other people, it may not be what my definition is. And so we need to come together and have that conversation, particularly lawmakers.
As we were talking about before the lecture, some of the great discoveries recently have been by people that are trying to do A and discover that B. Well, Penzias and Wilson is one of the real characteristic ones, but there are many others.
Yes.
Oh, tons of them.
Yes,
I have
all the
a
time.
bunch of stories associated with whatever.
Many
you
others,
present.
and so.
This is supposedly the nature of science.
Yeah.
In other words,
Absolutely.
you don't know what you are going to get.
Well, you're trying to get something. You think you are trying to, like Ray Davis just wanted to see whether he could discover neutrinos from the sun. And then later he found out it didn't match the theory. And it took decades to figure out, and won him a Nobel Prize, and oh yeah, it doesn't match the theory, but there's a good reason, something else.
Yes. That's anyway, so I agree completely. It's that's why I give the condensed perspective, because it gives.
Sir, yeah.
Yeah. I was a bit, as a physicist having moved into philosophy, I was a bit wondered what your project was. Because, I mean, discoveries, inventions, so on the one hand it seems that you wanted a definition of what science is. On the other hand, and I think rightly so, you sort of criticize the static vision of what science is, because often in the fights with critics of science or pseudoscience, like for example creationism,
Yes.
their strategy is to require or give themselves a definition of what science has to be, namely absolutely completely explanatory, and then since this cannot be achieved, so here's an alternative that looks equally plausible.
Yes.
So I wasn't sure whether in fighting with concepts that are good for journals like Breakthrough,
Yes.
Discovery,
Yes.
you were sort of posing yourself a problem that you actually didn't want, because you were emphasizing against science critics the openness of the scientific process.
So I think I hit my mark then, at least with you. You know, I think I've been successful, because it gives you pause to think about it again yourself, and maybe colleagues later that you'll chat about. So I'm not trying to project an absolute definition here and the rest. I certainly have one for myself, but it's based upon my own cultural and life experiences. I think everyone else has their own, but at some level, when we come to work in a laboratory to look for axions, or to look for understand sound or superconductivity, we have a common ground where we meet, and a standard by which we test ourselves. But yeah, it's observational and theoretical. It's just not observational. And so it's a challenge. It's a challenge because molecular genetics would like to be where we are with so many equations and discussions, but I'm just dumbfounded by the number of variables that they deal with, not like the proteins and the rest. Having lived with my life, been married almost 40 years now, so it's amazing.
Yeah, I have a question. So, like, all these, I agree with this point of the science, and also all these covers, you say, like, breakthrough, like, it's like, I discovered A, I discovered B, I discovered C, I discovered 3. There is all, but what happens, what is your standpoint in terms of, like, null results, right? So it's a lot of science in not discovering things, or not observing something, but we tend to not publish them.
That's correct.
Or
yes.
not sharing that information, and then we are having other teams repeating the same experiment, and like we're
Oh,
repeating the same
excellent. So this happens a lot in molecular genetics also. So the National Science Foundation has targeted the National High Magnetic Field Lab to be one of the premier introducers of rigorously enforcing their approach to fair practices of data. Findable, accessible, interoperable, and readable is fair. And having those data sets, not just the ones that are published in the paper to make those plots, but the others that were then discarded and not a part of what you're doing. The famous example is Millikan, the Millikan oil drop experiment, where he says that I've published all this, these are all the data that I've taken. And he wins a Nobel Prize. And then he passes away. And then his lab books go into the archive. And the archivists go to work, and they find out that there's a large number of data points that he did not include and gave no explanation for doing it. And yet he wrote in the paper that was published that these were all of the data that he acquired. And when you actually include those data that he excluded, you get closer to the value that we have today. And then the sociological impact of that particular event with respect to Millikan's value was called out in question by Feynman when he gave the commencement speech to Caltech one year, and it's publishable, and it's called Cargo Cult Science. And Cargo Cult Science is based upon the idea of, oh, since they already found this number, they must have been right. So if you then plot the value for the charge as a function of time of Q, and this is today's value down here, you find the value up here from Millikan, and you find something that does this eventually, and it converges like this as a function of time. And the only way that could have converged as a function of time is that Feynman didn't call out Millikan explicitly. He called out these individuals particularly these individuals, for probably not even admitting that it could actually have extended down to here and been so that they could have been so wrong and the rest. And once again, that's when do we teach ethics to our students? Yeah. When do we know that integrity is important? Now, you might say that integrity is not important, or ethics are not important. But these are the issues that we need to discuss as a group, to be prepared to talk to people who are not scientists, who on your own Capitol over here or in Washington are making decisions.
I mean, we have a discussion a few years ago. I was in Stanford before I came here, and then you know what happened with the president of Stanford several years ago.
Yes.
So he basically like faked all his work for the past 15 years or
Yes,
so,
yes.
right? So, and it was a lot of work behind that, right? And then that opens a discussion to the public, say, oh, if this person, which is like a president of an Ivy League university,
Yes.
does that, so why should we believe science?
Yes.
Whatever definition
Exactly,
of science is,
exactly,
right?
exactly. Have you
Because
counted that
those are
question?
the ones that make the public and go to the public, those news. And of course we have these break news, but they're not as sensationalist as can be that the president of a big university is being accused of falsification of Alzheimer.
Millikan's name is, Tom Rosenbaum, president of Caltech, has removed Millikan's name from all the named lecture halls and buildings at Caltech. Millikan was the first president of Caltech. It's not because of this specifically, it's for other reasons. But these are the reasons that we should be asking ourselves about recognition of science, the results of others, the culture that we do the work in, that how do I treat other people with respect and listen to their voices even if I don't agree with them. This is where we'll build trust with the public about the results of what we get, the message we really want to get.
But is that science?
Oh, that's the right question. Yeah? So is it acoustics I learned today is the brain, the neurology. I don't a larger list of important. It's a synthesis. It's a melting pot of many things, and so is science at some level. Yes, please.
I want to say, any situation where you have a controversial experiment, then the safest thing is to have the press present. And so the next week, that's what happens. There'll be video recording everything, interviewing the scientists, the subjects, and so on. And when this company decided to do it, I was asking why. But actually, after your talk, now I realize it has to be done because of the very controversial nature of the experiment.
The challenge of the people,
recording everything.
the challenge of the junior people in this room is the AI being able to fabricate even false narratives and pieces of data, and as I mentioned earlier, I couldn't believe what the newspaper or what I heard NPR tell me on the radio. So I found a video clip of DeSantis as governor saying something, and I took that as real then. That was a couple of years before AI really hit the big the big explosion. But I have to be careful now in the future to know that that's not fabricated, that there are these tools that allow that to really mimic those things.
Marsha? So I have a question about the fraudulent discoveries and so on. Do you think because in pure physics there is not as much scope for commercial benefits, etc., that it's less prevalent? And also as a function of time, do you think we're getting better at avoiding?
So I do. So let me answer the last part first.
Okay.
I think the recent history with the things that Nature published, Nature knew that one paper from the high temperature room temperature superconductivity was already being scrutinized. They went ahead and published the second paper. I was at the APS March meeting in Las Vegas, and I went like this. It was accepted on the day that he talked at the March meeting.
Yes.
I couldn't believe it. I couldn't believe that the editors didn't hold it. And the only conclusion that I can come to, even today, is that nature is a commercial enterprise, and even bad press is good press and sells magazines.
Right.
And so then we can charge more money for people to pay to try to publish that.
Right.
And I think I tell junior researchers that's not the right message. I talk about Albert Fair, for example, winning the Nobel Prize, and he was published in Phys Review B. And I was a postdoc in Saclay, or Essay, I should say, and Maurice Chapelier's group would have lunch with the Fair group, and I heard Fair at the lunch table having conversations about how he had a really neat result, but he couldn't get the funding from the French funding agencies to fund it. And it was the stuff that won him the Nobel Prize at the time. And I thought, wow, this is really amazing stuff. So Phys Review B is fine. Publishing your work with integrity, with the voice, with responding respectfully to the referees, but also understand that if the referees aren't getting it, maybe it does need to be written so it can gather a bigger audience. This is the Happy New Year. I just realized this is the Happy 2025 colloquium for this department. This is the message of all the colloquiums to come, is how is this going to make us better scientists, or help our work, or make us a better society, even globally, for example. I don't want to take, I don't have to.
So this is a long discussion. Really appreciate everybody, particularly our speaker. Let's take one more time. Good. Yeah.
Your magnificent voice was just about to run out.
Yeah.
Next week, Stanton is coming.